Number 2 says, find the linear approximation of f of x equal to sine x at this point, x equal to pi over 3. It used the approximation to estimate 62 degrees. So what's interesting about this question is we have degrees and we have radians mixed together. So I want to point out that we have degrees and radians mixed. So ultimately, we want radians. We always like to work with radians. Okay. So I'll worry about that a little bit later. But, you know, we've got to write down a few things here. So one thing we need to do is we need to know what our A point is, the anchor point where we're doing our linear approximation, that anchor point where we're calculating the equation of the tangent line. And that's going to be pi over 3. We want to identify what our function is. Our function f of x is going to be sine of x. We're always going to need to take a derivative. So we'll calculate the derivative. The derivative of sine of x is cosine of x. And then I want to evaluate both the function and the derivative at each of those points. So we're going to have f of a is equal to f of pi over 3. You need to know what sine of pi over 3 is. What's sine of pi over 3? I'll give you a choice. It's either 1/2 or rad 3 over 2. Any thoughts? No thoughts. Okay. So I could draw a little triangle here. The shortest angle is pi over 6. The longest angle is pi over 3. The longest side is 2. The shortest side is 1. The other side is rad 3. Sine is opposite over hypotenuse. Rad 3 over 2. Make sense? Let's calculate f prime of a. That's the same thing as f prime of pi over 3. That's cosine of pi over 3. I hope you guys studied the unit circle. You know the rad 3 over 2 and the 1/2 always come in pairs. So if that guy's rad 3 over 2, this guy is 1/2. So since I have all that, I can tell you that our linear approximation formula is going to be the y value at our point plus the derivative at the point times x minus a. It's just a modified point slope formula. Now I'm going to plug in the pieces. F of a was rad 3 over 2. F prime of a is 1/2. Now here's where things get interesting. Well, I'll just write in x minus pi over 3. That's our linearization formula. Okay. Any questions so far? So I want to calculate the linearization at 62 degrees. So if I have L of 62 degrees, what is that going to look like? That's going to look like pi rad 3 over 2 plus 1/2. And then I'm going to have a 62 degrees in here minus pi over 3. Do you guys remember how to convert radians to degrees and vice versa? Let me remind you in case you forgot. Pi radians is equal to 180 degrees. Okay. So if you wanted pi over 3, you would just divide both sides by 3. So pi over 3 radians is equal to 180 degrees over 3. That's equal to 60 degrees. So I could really write in 60 degrees here. But I don't like it because I want to work with radians. So this result is going to give you 2 degrees, but I want to change that 2 degrees to radians. So how can I do that? Well, if I took my pi over 80, I'm sorry, my pi is equal to 1/8. As I said earlier, pi degrees or pi radians is equal to 180 degrees. If I divide both sides by 90, then I'm going to end up with 2 degrees on the right-hand side, and I get pi over 90 on the left-hand side. Or you could do, I guess the traditional way you do it is pi over 180 is equal to 1 degree, and you'd multiply both sides by 2. Maybe that's the better way to think of it. Okay, but it all kind of this basic identity and just manipulating that. So my point is that our linearization is going to give us a pi over 90 like this. So we're going to have rad 3 over 2 plus 1/2 times pi over 90. And that's going to be our answer. And if you wanted to, you could stick that into a calculator to get a decimal result. But this is our approximation. So, the first example here, this was just trying to capture the idea that we need to choose the A that's close to 16.1. So 16 is a good choice of A. The second example emphasizes the difference between working with degrees and radians. We always want to work with radians. Is there any questions about these? Okay.